Please wait a minute. Okay, seems like classroom very busy now, so it will need more time to open the lecture note there.
Sir?
Yes?
To avoid some misconception, I mean communication, do you mind naming those for students?
Pardon?
Do you mind those for students?
Okay. After the class, I will mention the name of the student who have not submit their assignment.
All right, sir.
Okay, so I will start the lesson now. Okay, can you see the slide here?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, good. Okay, so let's start now. So repeat join is kind of conventional join. Why we call this conventional? Because it is already developed a long time ago. So it's kind of traditional join. Okay, but the technology is not traditional now. It's still growing. So it's still evolving. Okay, because the technology always provide a new method to join the mechanical part. So it's kind of very interesting topic to discuss about join in mechanical building. Okay, so I think you already know about this kind of join, especially when you pass the bridge and you maybe capture something in the structure and think about how this bridge was made, and maybe you see many sticks, not sticks, but many points arranged in fashion way, not fashion, in defined pattern to combine between the beam, between the part of the bridge. And maybe later we can see the picture of it. And here you see what rivet is. In the first figure, we have the rivet part. So this part will be used to join, to clamp the mechanical part. It can be steel part or steel plate. It can be aluminum plate, okay, or it can be composite. But for composite, it is required very special refit. But for steel and aluminum parts, we can use common refit body. So here you see this refit composed from head, body, and tail. And in the second figure, we have two plates here. This is the first plate. This is we call the adherent or substrate. That is the component that will be joined. And this is the first plate. And here we have the second plate. Then we make a hole in both plates and then put this refit body inside the plate with the head in the bottom and the tail in upper position. Then you put the die here. It can be in high temperature or in room temperature. So maybe the temperature can be increased in order to melt this tail. So when this tail is melting because heated and you push with the pressure on the die, it will form the tail just like the shape of this die, okay, following the shape of the die. If there is no thermal heating, then usually it is rotating like this. The die is rotated because they want to use the friction between the dies and the tail to increase the temperature of the refit. So if the temperature increases, it is easier to form the refit following the shape of the die. Okay, so that's how the refit used to combine or to clamp the mechanical parts. Usually, it is this mechanical part to be joined has a large surface area because it is required enough space to put this refit into the combined part. Okay, so that's how the refit joint made. And here you see the example of the application of refit joint. And here we have very good example. We have the airplane here. This is the head. And this is the wing. And you can see here, there are many rivets on the body of the airplane. So it's kind of, there are many aluminum plates stitched up together to form the body of the airplane. So it is, it used many rivets here on the body. not only for aircraft or airplane, but rivet also used to build the boiler. So if you ever seen the boiler, it is like a tank, cylinder tank, like this, which is made from the steel, just like the aircraft. The body is made from plate, from steel plate, and steel plate is joined together by rivet joint, like this. It is also stitched up to form the cylindrical body from the tank. Okay, so this both the rivet on the airplane or in boiler receive some load, actually very big load. So this rivet uh, must keep each part to stay in its original position without deforming, without displaced, or without fracture. So actually this kind of joint is very strong. Okay. And also in the boiler, it has a very big pressure inside this. Very big pressure working in all directions. So therefore, for this kind of joint, for rivet joint, we have the standard. It must follow the standard to ensure the safety and the function of this joint, the strength and the safety of this joint. So that's how we apply the rivet joint in the real mechanical building. So for the standard, just like we discussed in our previous meeting, we have many standards that can be followed. Okay. ISO and ANSI only two existing standards for rivet joint. Okay, our session will be end by 10 minutes, our first session, but please join again using the same link, okay? If this Zoom is closed automatically, then please rejoin again with the same provided link. Okay, let's continue in 10 minutes. Okay, so how we learn to design the rivet joint. So first is we have to know that there are many types of rivet joint. Okay, and here we have 3 examples of rivet joint. The first is we call single rivet lap joint. We call lap joint because it is overlap each other. The first plate is overlapped on the second plate. And this is the overlap area. Okay. Because we only have a single column of rivet, then we call this single rivet lap joint. So to increase the strength of the rivet joint, we can put another column of rivet lap joint. Okay, we can put one more column of rivet on the overlap area. So that we call this double riveted joint. Okay. So let's make a note here that for single rivet joint, we have spacing distance between rivets, and we call this as a pitch. Means the distance between the center of the rivet with another rivet in sequence, the closest rivet. And here we also have, for double rivet joint, we have pitch and we have another pitch between the columns. We call this base pitch, which separate these two columns. And if the arrangement of these two columns is not in line, so this pattern is in line each other. But if we change the position of the second column, just like in the figure C, then we have the zigzag riveting. And here we change the pitch between the column because it is not in line. So it creates a diagonal distance like this. What does the effect of this pitch? In the standard, it is defined that the pitch between the rivet must not less than the allowable distance, a certain described distance in the standard. Because if we put the rivet too close each other, then it can create the failure between this rivet. So it has minimum distance. Okay. And this minimum distance must follow the standard. Okay, later we will understand why this distance very important. And the meaning of this pitch is, the other meaning of this pitch is that we can make the calculation become simple. So, for example, as I mentioned previously, if we have a cylindrical tank, like this, so for example, this is an LNG tank, and it is not welded, but it is riveted around this circular area. Okay, around this circular area, and this is the center. Okay, this is the plate that overlap each other. And here we have many rivets. So if we cut this cylinder, at this side and open up the the whole structure, then here we have something like this. If we remove the cup, this and cup we remove, and we cut in this line and open up the tank, then we have this kind of uh, structure. Okay, so this is the cutting line. Here we open up, and this here we have the rivet joint around this. Okay, so and this is the overlap area. Okay, so pitch means if we can describe the load here, and we have so many rivets lay up in this joint, we don't need to calculate all of them. We don't need to calculate one by one. The stress in the rivet is assumed equal, homogeneously distributed. So the load is assumed to be homogeneously distributed on each rivet. So in that case, we just need to focus our analysis in this part only. We can only take this part in our calculation, and it contains only single row of rivet like this. Okay, only has single row of rivet, and it can contain only single or double rivet. Okay, it can contain one rivet or two rivet. So how about this load? Yes, it is distributed over this whole area. So if we only take this area in our calculation, so this P must be divided by the number of rivet here. For example, along this line, we have 100 rivet. So we just take this area only. Okay, please wait for the others. Okay, thank you for joining this class, and let me repeat my explanation, my previous explanation. But now I will use whiteboard first. So let me explain again. If we have a cylindrical tank, so this tank made from the plate, which is combined or joined by the rivet along its side. And there is the pressure work in this uh, tank in all direction. So if we slice or we cut this tank and open up, so this is A and this is B, and we open up this tank, and here we have A and B, and here we have the joined part. Okay, and it consists of many rivets. It is joined by many rivets here. And here we have a distributed pressure. We call this P. And in order to analyze the strength of this joint, we don't have to calculate one by one along this row, because it can contain hundreds rivets in a single line. So if we calculate one by one, then it will take a lot of time, require a great effort. So how to calculate this kind of joint? As I mentioned previously, we assume that the load is distributed equally, homogeneously. So we assume that this load is distributed homogeneously. So that's why each part of this rivet will receive the same load with the other part. And here, the load must be divided. So if the overload equal to P, and here we have 100 rivet, the number of rivet is 100, then we have to divide this load by the number of this rivet. So for example, here we have 10 kilonewton, then here we have 100 newton, okay, after divided by 100 rivet. So each rivet, so each part of this joint receive this load, only 100 newton. And how to know the total capacity of this joint? For sure, by multiplying with the number of rivets. So we just only analyze this isolated area only. No need to calculate one by one. And here the pitch become important, okay? Because we call this is one pitch area. Only in a single pitch area. we make calculation only in a single pitch area. No need to do calculation in overall area. Okay. So can you understand this?
Yes, sir.
Okay, thank you. Okay, if there is no question about this, then I will come back to classroom. Okay, so now you already understand the meaning of pitch. So for this, sorry. So for the first joint here, the direction of load must be here, and it is analyzed only in a single rivet. So this is cut in this section. Okay, and this is the second plate. This is the first plate. And you see here, it contains only a single rivet. So that's why we call this single rivet lap joint. And for next, here we have, for single pitch area, we have two rivets. Okay, this is the second plate, and this is the first plate. And in the overlap area, we have two rivets. And here we have the loading per pitch. This is the load for a single pitch. And also for the third zigzag riveting. Here you see another type of rivet joint. It can consist of 3 rows. We call this chain riveting. And in this slide, it is shown another notation. Here we have M. We have M, which describes the minimum distance from the center of the first rivet in the row with the edge of the plate. And it has minimum distance. It must not smaller or not less than 1.5 the diameter of the rivet. Why? Yeah. If we put this rivet too close with the edge of the joint, then it will start to crack like this. If we put this rivet too close with the edge, it will initiate the crack that will grow and tear apart the plate. So that's why M here is an important consideration in the design of a rivet joint. And in the standard, it is described that this M minimum distance is 1.5 the diameter of the rivet. Okay. And for the last figure, here we have another type of joint. Here we see this is the main plate that are connected each other. But instead of using the overlap, which not lay in a single plane or not in line. So the center line of the first plate and the second plate is not coincide. This type use this I mean for the lap joint there is a disadvantage. Okay. So the load because the center of the plate is not coincide, so the load will create moment because it has eccentric distance. It has distance between the first and second load. And because this eccentricity, it will create the bending moment. So this joint tends to bend like this. So in consequence, it will become like this. The joint will become like this. And this is not good. This is not good design. Okay. So in order to avoid this kind of problem, to avoid this kind of eccentricity, some designer choose the butt joint instead of lap joint. Butt means this the combined plate can meet each other in a single line. So, butt in bahasa Indonesia is pantat. Jadi pantat bertemu pantat di sini. So that's why we call this butt joint. Okay. So now after we remove this eccentricity, then we can keep this joint structure to stay flat, not bended. Okay. But in order to have this kind of joint, we have to add another plate. We call this cover. Okay. We have two covers in the upper and lower side of the plate. Okay. And we put the rivet between them. Okay. And here we call this double cover butt joint. Okay. Because we have two cover and two row of rivet here. Okay, so the main point of this slide is first that we have to consider about the minimum distance from the edge of the plate. And next, for other type of joint, that is butt joint, we can avoid the bending moment created by the eccentric load by keeping both plates in line. Okay, so that's the main point. Okay, for butt joint, double cover butt joint, there are also many variants. Okay, so here we have chain riveting, zigzag riveting, and other type of joint. So when we design the rivet joint, we have to take a look about the requirement of the joint itself. So the characteristic of load, I mean. So if it is allowed to have a little bending moment, then we can use lap joint. But if the bending moment is out of consideration, then we have to choose the butt joint design. And when to use the single rivet or double rivet, it depends on the efficiency of the joint required. Usually, double rivets give us better joint efficiency or joint strength than single rivet. Okay. Next is the manufacturing process. Okay, so after we put rivet, we have to put another process, which is called caulking and fullering. Okay. So the purpose of this caulking is to prevent the leakage. So if here we have high pressure steam, just like in the boiler, or high pressure gas, just like in the LNG tank, so the leakage is not an option. So there is no leakage allowed. So that's why this caulking is required, because it can close the gap between the head of the rivet and the plate. So by doing that, we can prevent the gas to flow inside the gap. And fullering tool is used to reduce the stress concentration in the edge of the blade. Okay, this is just an additional information about the manufacturing process of the rivet. Okay, so this is the main topic in our discussion. So how to calculate the strength of the rivet? In order to be able to calculate the strength of the rivet, please wait a minute. It's noisy here. Okay, sorry for that distortion. Okay, so in order to be able to calculate the strength of the joint, then we have to understand the failure mode of the joint itself. So the first failure mode is crack or tearing, because we put this rivet too close with the edge. Okay, close with the edge. Then we create or initiate stress concentration here, and it will create crack which can grow up to the edge. Okay. We don't have to calculate this because it is already described in the standard. It is based on a very long and proven research. So we just follow this standard. So make sure to have enough space to put your revamp in the joint. And next, that's what we have to calculate is the tearing. Okay, so for the next part is also tearing. It's also crack on the plate, but it is not caused by the stress concentration, but it is caused it is happened because we have the load here create the tension stress on the plate. Okay, so this key load create the tensile stress here, and when the tensile stress is larger than the ultimate stress of the plate, then the crack occurs. It will broken the plate. It will broken the plate across this area. So that's why we put the calculation like this. So the maximum tensile load, the maximum tensile load that work on the plate can be calculated like this. Here we have the tensile area, okay, multiplied by the tensile stress of the plate. So this is come from the material of the plate. This is plate material, and this is the geometry of the joint. This is the tensile area, the effective area of the plate that hold or resist the load. And the area of the plate, here we have the thickness in this direction. Here we have the thickness T. So the effective area of this crack area is this length multiplied by the thickness of the plate. And here, for example, we analyze the joint in a single pitch. So we take the joint in this area only. Then the total length of the plate is as long as this pitch distance. But in this single pitch, not all area is filled by the plate. Here we have the rivet occupied the space for this area. So the effective area is pitch minus by diameter here. So this is the effective area which holds this tension load. Okay. So that's why Here we formulate the effective tension area for this single lap joint as P, the pitch distance, minus by the diameter of pitch multiplied by the thickness of the plate. So please keep in mind that here we calculate only in a single pitch area, not for all the joint area. So if we have in this line, in this column, the pitch, the number of rivet is 100, then we have to multiply this PT with the number of the rivet to have the total load working on the joint. Okay, can you understand this? Is there any question about this steering failure?
Sir, I want to ask you some questions, sir.
Yes, Edgar, please.
I rather confused, sir, if the rivet joint can bending, sir, but it can shearing, sir. What is solution for shearing joint? And one question again, sir, like what is the standard for rivet joint, sir? Can there is ISO, there is NC. What is the kind of the standard requirements, sir, for that? Yeah.
Okay, so for the standard, you can choose to use one of them. Depends on your customer and depend on your company. Okay, you have to follow their requirements. That's for the standard. You can click the link I put in the classroom in the previous slide to check each standard, and they will describe everything about the rivet joint. And about bending moment, as I previously explained, for lap joint, if we can make sure that the plate being joined is very thin, then maybe we can minimize the effect of bending because of the eccentricity of the load. But if the plate being joined are thick, then we cannot how to say, we cannot ignore the bending effect. Okay, or even if we use very thin plate, it still has an bending moment. It still has bending moment work there, even it is small. And even if it's small, it still can bend the plate because the plate is very thin and become very elastic. So if we want to avoid the bending moment in the joint, we cannot use single lap joint, must use butt joint. Okay, so that's about the bending. And usually this bending effect on the failure of the joint, we don't calculate this kind of effect because usually we just add the safety factor in our calculation to compensate this bending effect. Okay. So we just put a safety factor. And about shearing effect, yes, we will discuss it later after this steering. So this fracture on the plate due to tensional load, it's just a one failure mode. But we have many failure mode for this rivet joint. It can help you, Edgar.
Yes, sir. Thank you very much.
Okay, you're welcome. Okay, let's go to the next slide.
Sir, I want to ask a question, sir.
Okay, please, Ihsan.
Do we only calculate the place in between, sir?
Pardon?
Do we only calculate the place in between?
Yes, the distance here. Yes.
Yeah. So if there are, 100 rivets, so there are only 99 area.
Okay. If it is a circular, maybe yes. Yeah, maybe yes. But usually in the design, we just multiply by the number of rivets. So it is okay.
If the case is like this, is this counted as 1 or 2, sir?
The rivet.
Yes, in the right picture, there are 2 rivets, right?
Yeah, but we take only the half of them, right?
Oh, okay.
So that's good question because it can emphasize the meaning of pitch. Pitch is measured between the center of the rivet in the square. So that means it contains only a single rivet, right?
Yes.
Okay. So that's the reason. Good question, Iksan. Thank you.
Thank you, sir.
Okay. You're welcome. Any other question?
Yes, sir. I want to answer something, sir.
Yes, Sultan, please.
In rivet, we know that there are many types of rivet, sir. So the calculation is used for all, sir, or
Yes,
just
actually, this the difference between each rivet is the type of the head, but for the body, it's always the same because it is following the standard. Okay, I know what you mean. Maybe this is what you mean, Sultan. So maybe we have this kind of rivet, or maybe we have this kind of rivet, the head, or maybe other type of rivet. Is that right, Sultan? Then,
yes, right, sir.
if there is many kind of rivet, is like shown here, then how to calculate each of them? Actually, this is the same because we use the same body. This must follow the standard. That's why the standard is very important. Okay, so the point is the method to calculate the strength of the rivet joint does not depend on the type of rivet, but depend on the material of the rivet and the geometry of the joint. That's the answer, Sudan.
Okay, sir. Thank you very much, sir.
You're welcome. Okay, so next, the joint failure number 2 is due to shearing. So usually rivet is made from steel or aluminum or copper, which is ductile. So ductile material is very sensitive with the shearing stress. It can resist very big tensional stress or compressional stress, but it is weak. It must resist the shearing load. So it's kind of the weak part of ductile material is the shearing load. So that's why it is included here as a joint failure. Okay, as mentioned by Edgar previously, that the rivet can be sheared apart due to this eccentric load. And as you have to make a note here that for a single lap, we only have a single shearing area here. And for a single cover butt joint, we have two shearing area on the rivet because we have two rivets. Okay. And for double cover butt joint, here we have four shearing area. And of course, if we have more shearing area, means that we can apply larger load here. Okay, we can apply larger load because we have more shear area. So that's why the load, the maximum load that can be applied on the joint based on this shearing failure, it depends on the number of the rivet in a single pitch. It depends on the number of pitch. And for this first formula can be applied for single lap joint and single cover butt joint. So it depends on the number of rivet only. But for the second formula, it can be applied on the double cover butt joint. We put number 2 here to mention the number of shearing area because we have two shearing area for a single rivet. Okay. So for, just in this case, we have two rivet, and each rivet has two shearing area. Then here we have four shearing area. And this shear stress is the properties of this shear strength is the Okay. Thank you for joining again. So to repeat my explanation, here we have the searing failure mode, and to be noted that for each type of joint, it has different shear area. So for single lap joint, we only have one rivet area per pitch. Okay, and for single cover butt joint, we have two because we have two rivet there. And for double cover butt joint, we have two rivets, but we have four shear area. And knowing this case, then we can make sure that this type of joint has the larger shearing load capacity because it has more shearing area. But be careful about these two multiplication. Even though we know that these two came from the fact that we have two shearing area here, but in the standard, several countries reduce this number by 1.5 or 1.85 or 1.8 like this, because maybe they found that it is actually not correct to put two here. Even theoretically, it is true, but maybe because of the deformation during loading, it has necking here. So maybe the body of the rivet shrinkage like this. So the shearing area becomes smaller. So that's why they put this value instead of 2. Okay. And usually this kind of standard used for boiler. Because boiler have very high temperature, so this temperature can deform the shape of the rivet. So please be careful about this if you design the boiler or the part which operate in high temperature. Okay, so next, other joint failure that is crushing or bearing load or bearing stress. So please observe the shape of the hole on plate. Okay. Here we can see that the circular shape deform and change into the ellipse because of this tension load. Why this can happen? Because the rivet crush the plate and the plate deform. Okay, so this is also kind of failure because if we have the deformation here, it can open up the joint. So it creates loose, create gaps between the rivet and the plate. And if the rivet and the plate become loose, then it can open up and create failure. So therefore, we have to consider this in the calculation. Crush failure can occur or happen in both the rivet and also the plate, both of them. So the deformation not only on the plate but also in the rivet area. Okay. So choose the weakest of them, the weakest material of them, if they have different type of material. But if they are made from the similar material, for example, steel, and this is also from steel, then calculate one of them is enough. But if they have different material properties, then we make two calculations here, one for the rivet and one for the plate. Okay, so for example, if the crust occur in the plate, then we check the properties of the material of the plate here. The crushing stress or compression stress. And here we have the crushing area. The crushing area is the projection of the contact area. Here the contact area is half of a circle, but the projected area is actually here. So here we have the diameter. And this plate has the thickness. It has the thickness. Okay. So it also has the thickness here. I will redraw here. This is the length and this is the thickness inside. So this is the crushing area. And this crushing area is the diameter multiplied by the thickness for single rivet. If we have more rivet, then put N here. If in a single pitch we have several rivet, N number of rivet, then put N here. Okay, so we already talked about the failure mode of the rivet joint, that is tearing of the plate, shearing of the rivet, and the crushing on both plate or rivet. Okay, so we have three kinds of failure mode: tearing, shearing, and crushing. Mbak, tolong pintunya ditutup, Mbak. Makasih. Okay. So to define the efficiency of the joint, we have to calculate the three of them and choose the weakest or the smaller one, the smallest load. Okay. Choose the least, the smallest load from these three and compare with the plate without joint. Or full plate. So that's why for a single pitch, the full plate area is the pitch distance times the thickness of the plate. multiplied by the tensile strength of the plate. This is the load capacity for plate without joint. So the ratio between the weakest load calculated from the failure mode to the plate without joint, we can obtain the joint efficiency. Okay, so that's the theory behind the failure analysis. Okay, so next, here we have some examples. Okay. We have some example. Okay, so here we have several examples. Okay, so the weakest part will determine the overall strength of the joint. Okay. That's the meaning of efficiency. The efficiency will be determined by the weakest load capacity. Okay, so here, for example, we have overlap joint here, and for single pitch, if we I think we have to see the problem first, not the solution. But it is disappeared. Okay, so the problem is that we have a single lap joint here. With single reset, and we have load working here, and we know the properties of this plate. The ultimate tensional strength is 400 megapascal. And here the diameter of the rivet is 25. Okay. And the pitch distance is 75 millimeters in millimeters. And the thickness here we have 15 millimeters. Okay, so for the first failure mode is the tearing of the plate. Okay, the tearing of the plate. Here we have the tearing of the plate. And we can calculate the tearing area. And we can multiply by the tearing, the tensional stress of the plate, and obtain the load capacity that allowed by the tensional strength of the plate. If the working load larger than this 300 Newton, 300 kilonewton, then this kind of failure will be occurred. Okay, the plate will be broken if we apply the load larger than 300 kilonewton. And how about the shearing? Here we have single, we have, oh, maybe this is not single up joint, but because we have here two. Okay, okay, I have to check the problem again, but the shearing resistance of the rivet per pitch is N times the area of the shearing and times the strength, the shearing strength of the rivet. Okay. So here we have two. So means that we have the shearing area. Okay. And the capacity is 314 kilonewton, 314 kilonewton here. And for the crushing load, maximum is 480 kilonewton. So the main point is which one describe the overall strength of the joint, that is the weakest part. So here we have only 300 kilonewton. So this will determine the strength of the joint. Okay. And for the real design, we have to put the safety factor. This 300 kilonewton, describe the maximum capacity, the maximum load capacity. But because there are uncertainties in the material, in the manufacturing process, in the design itself, we have to compensate with the safety factor. We have to make it smaller. Okay. So, for example, here we have the factor of safety is 4. Actually, 4 is very big safety factor. It can accommodate the dynamic load, the impact load. Okay. So here we have the final specification for our joint is 75,000 Newton or 75 kilonewton. Okay. So this will be written on the nameplate of the product. Okay. So this is the specification for customer. Even though we know that this part or this joint can hold up to 300 kilonewton, but the customer only know that it can be applied with 75 kilonewton only, because we put safety factor here. Okay. So for the user, it is 75 kilonewton. Okay, so after we know the actual shearing resistance on the plate, so this is we call actual, and this is the allowable. Okay, so 300 kilonewton is the allowable, by the material, and the 75 kilonewton is the actual load. It can be applied. So other stress can be calculated based on this load. Okay. So for the shearing resistance so can be calculated using this load. So the working stress on the plate will be 100 megapascal. So if there is rivet here, the stress, the working stress here will be 100 megapascal due to 75 kilonewton of load. And as we know from the specification of the material, that this material have the strength of 400 megapascal. Now, because we use the safety factor of 4, then it is divided by 4. That's why it becomes 100 megapascal. Okay, for this first example, is there any question?
Sir, I have a question, sir.
Yes, please speak it.
How do we know the number of rivets per pitch? Because in some problem, I found it 1 and the other I found it 2.
Yes, it depends on the name mentioned by the problem or the figure that shown by the problem. But for this example, it is my bad to I forgot to describe clearly the problem. It's go directly to the solution. Actually, here we have problem description first, but it is disappear. Maybe I made a mistake during editing this slide. Okay, so here actually we have drawing which describe the geometry of the joint. Okay, can I help you, Pipi?
Yes, thank you, sir.
Okay.
I think that's clear.
Please, please don't be worried about that, because next you will have clear problem description. Okay, if there is no question about the calculation and the concept, I will continue to the next example.
Sir, excuse me, sir. I want to clarify something.
Yes.
In the shear failure, there is a shear area, sir. I want to clarify something. We know that the shear area is 1 of 2 is depend on one rivet, kan, sir?
No, but also depend on the type of joint also.
Oh, I see.
Put the number and the type. Okay, I will repeat again because it is very important. Okay, so for the first and the second figure, we have different calculation of shearing area because the number of rivet, right? For the first figure, we have single overlap joint, only one rivet and only one shear area. But for the second figure, because we use butt joint with single cover, so we need 2 rivet to make this kind of joint. Because we have 2 rivets, then we multiply the shearing area by 2. Okay, so the point is that for this first formula, for this first formula, it depends on the number of rivet. Okay. And the number of rivet depends on the type of join. For this butt join, we cannot use single rivet, because if we use only this rivet, then this plate will go away when we apply the load. So in order to maintain this plate in its place, so we need another rivet. So we put 2 rivets in this single pitch. So that's why we put N here, because sometimes it consists of 1, and in other case it consists of 2 rivets. Okay, and if we use double cover butt join, just as shown in the last figure, then we have 2 rivets and also have 2 shear area for each rivet. So that's why we put another constant here. We have 2, which come from these 2 areas as a consequence of using double cover butt joint. That's how it works, Sudan. Is it clear for you?
Yes, it's really clear, sir.
Okay.
Thank you very much for your answer.
You're welcome. Okay, so that's how we calculate the load capacity for rivet joint. And for this example, the scenario is we first calculate the full allowable load that can be held by the joint. Then we put the safety factor in the calculation, which reduce the strength, because we divide by 4. And after we find the actual load, okay, the load that is informed to the customer, then we can calculate another stress based on this load. Okay. So I want to make sure that we understand that the actual load that can be held by the joint we design is 300 Newton. But because we want to make it safe for the user, then we divide by the safety factor. So here we have 75 kilonewton. Okay. It is much smaller. Okay. Then, if we want to calculate again the tensile, the allowable tensile stress, we have to use this load, not the 300 kilonewton. So this is the allowable stress. This is not the specification of material, but this is the working stress. And this is for the shearing stress occur in the rivet. Okay. And this is the crushing stress in the rivet and in the plate. Okay, so let's go to the next example. We have two different types of joint here. First, we have a single lap with single column of rivet, and next we have lap joint with double column of rivet. Okay. And with this example, we want to know the difference of the efficiency of each joint. Okay. And here we have the dimension of the plate and also the diameter of the rivet. And here we have the data of the strength of plate and rivet. Yeah. Okay, so everything already described clearly here. So let's continue to the calculation. We have the pitch is 50 millimeter. Okay, so this is the distance, the width of the plate that we use in the calculation. And for the first type of joint, that is single rivet, single lap joint with single column of rivet, we can calculate the tearing load, the tearing resistance of the plate is the width of the plate minus 1 diameter of rivet, because we use only single column there, and multiply by the thickness and times the stress of the plate, the strength, the tensional strength of the plate. So here we have 21 kilonewton, 21 and 600 Newton. Okay. And for shearing resistance, because we only put one rivet, because we have one column, okay, so one rivet per pitch. Here we have only a single shear area. This single shear area times the strength of the rivet material will give us 28,000 or 28 kilonewton. And about the crushing resistance of the rivet, because we have only one rivet, only one diameter times the thickness of plate, so only single crushing area, and we have 21 kilonewton. So among those three allowable load, which is the weakest one? So here we have 21 kilonewton, 28 kilonewton, and here we have 21 kilonewton. So the minimum is 21 kilonewton. Okay. And if we try to calculate the full capacity of the plate without hole, without joint, okay, the solid plate, so the area, the tearing area, is the pitch length times the thickness. This is the area, and then times the tearing strength of the, or tensional strength of the plate. So here we have 36 kilonewton. So this is the plate capacity, load capacity without joint. So by comparing or make the ratio between the minimum strength, the minimum load capacity of the joint with the capacity of plate without joint, then we can get this joint efficiency. Means we can obtain the strength or the load resistance of the joint 60% from the unrepeated or solid plate. Okay. And this efficiency is very low, only 60%. Only 60%. So people always try to find the method to increase this efficiency of joint. How about the next type of joint? Okay, to remind us, we have to check again the figure. So we put another row. So we have two row of rivets, another column of rivets. Okay, so now for a single pitch, we have two rivets. And now the tearing resistance, because it has pitch length change, becomes 65 millimeters. Then here we have the allowable load on the joint is 32 kilonewton. Okay. So we can see here that the number of rivets doesn't change the formula here. So let's check about this. Okay, sorry for this inconvenience because we are always interrupted by the time limit given by Zoom. But I hope that we still can focus on the topic today. Okay, so let's continue. So the question is why this formula doesn't change even though we put another column of reflex. Why we don't see the constant of 2 here? Okay, so let's see. Let's check in the figure. This is okay. So this is the pitch that we analyze. Okay. Sorry. It is already here. Okay. And for the next joint, we also have this kind of pitch. Same. Okay, so now let's see the load working here. And now let's check the tearing resistance. Here we have this tearing resistance working in this area, and here we have this area. Okay, and here also we have tearing area. If the direction of the load is like this, then in this side we will have the working load of P, and in this side also P. This side, because of action and reaction, is also P, and this is also P. Right? So in this case, the number of refract in this direction will not change the formula. Okay? Because for this area along the pitch direction, always work the same load P for each column. So it will not change the formula. Okay. What changes the formula is if we put another rivet here. That will change the formula, the area of the tearing. So it will not change in this condition. But if we put another rivet, then it will change here. We put N here, the number of rivet. Okay, so that's why the formula is still the same, even though we use another column of rivet. Can you understand this? Is it clear enough?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay, next. Thank you. So this is the first type of joint, and this is the second part of joint. It's still the same, but this difference on the load capacity is caused by the pitch distance, which is changed. Okay, it changed. Okay. And let's check the same calculation here. The tearing resistance due to tensional load is 32 kilonewton, and for the shearing resistance on the surface of rivet is 56 kilonewton, and for the crushing we have 40 kilonewton. And here we have the minimum one is the tearing resistance, that is 32 kilonewton. So if we compare with the load capacity of solid plate or unriveted plate, then it will be 69%. This is higher than the previous one, than the single lap joint with single column of rivet. Okay. Okay, so the difference is that the double column rivet can have higher joint efficiency. But let's see the cost to increase this joint efficiency. Okay. Of course, we have to put another column of rivet, so it will require more rivet on the body, and it requires longer overlap area. Okay, so the structure will be dense, more dense. Okay. So the weight, if we compare the weight between the first and the second joint type, we will have the second joint type much larger, much higher in weight, and the first joint is we can say lighter. Okay, lighter. Okay, so using this geometry, we know that this double rivet can increase the efficiency, but it requires larger overlap area. It becomes very dense, okay, compared to the first type of joint, and because it has more rivets, it requires more manufacturing effort. Okay. We have to make many holes, more holes, and put more rivets, and do more riveting. So that's how to compare the efficiency of joint. We can increase the efficiency a little, about 10%, 9%, but the cost is abundant, too much effort. Too much effort. Is there any question about this example? No?
Oh, sure.
Okay, let's continue to the next example here. Here we have double riveted with double covered butt joint. Okay, so this is the working load here on the main plate. This is just the cover. Okay, the cover to transfer the load from this plate to the second plate. And now we have the data, the strength, the permissible strength of each material for plate and rivet. And now we want to find the efficiency of the joint. So when we calculate this tearing resistance, there is no change in the formula, even though now we use double cover butt joint. Sorry, but the tearing resistance doesn't change. Okay, because for single pitch here we have load working here, and this is the tearing area. So doesn't change this tearing area. It's still the same with the previous design. And we have in the calculation the load capacity is 180 kilonewton. Okay. And the shearing resistance of the rivet, because we use double cover butt joint, so we have for a single rivet, we have two shearing area. And because we have two column of rivet here, we put another 2 for n. This is the number of rivet in single pitch. And this is the number of shearing area for single rivet. And now we obtain the shearing capacity. The shearing load capacity is 166 kilonewton. Next is the crushing resistance. So now we have two crushing area. It is clear from the figure that we have two crushing area because we have two rows. Okay, we have two not two rows but two columns. Okay. So for single pitch here we have two crushing area for each rivet. Okay, now we can obtain the crushing resistance is 150 kilonewton. So which one is the minimum? So it will be the crushing resistance. Okay, that is 150 kilonewton. So this strength will determine the overall strength of the joint. So we will compare this calculated strength with the full solid plate strength, that is 240 kilonewton. It is almost more than half. Okay, so more than half. That is 62%. So the efficiency only 62%. So according to you, which one is better among those three designs? First, we have single lap joint, and next we have lap joint with double column rivet, and the third we have butt joint. Okay. We have double cover butt joint. Among those three, which one has the higher efficiency, and what kind of additional process is required? What is the cost about this of each that join. So please keep in mind about this efficiency issue during design of the joint. So creating the joint or designing the joint with higher efficiency always in expectation. Okay, it is expected by everyone, especially by customer, but the cost to increase this efficiency is too big. The joint become expensive, and the customer will not interested if the cost is too big, too expensive. So you have to optimize between the joint efficiency and the cost. Okay, so this is our topic of today. But what we learned today only the joint with collinear load. I mean the load work in a single line. This load doesn't create any moment on the joint. So next, how if the joint geometry create the bending moment on the joint part? So for example, here, how if for next discussion, how if we have this first plate combined with this plate, and we have put the repeat, we put the repeat here, and the load is directed like this. This is not longitudinal load, but it is eccentric load because it has the distance between the center of the load, the center of the joint with the load. So it has eccentricity here. Okay. So this is will be our topic in the next discussion. Okay. So we still have about 30 minutes time left. Is there any question?
Yes, sir. I want to ask a question. How does rivet compares to weld and bolt, sir?
Rivet and bolt actually have similar analysis. Okay? Because the way it resists the load is the same, and the joint failure or failure mode also the same. So I think for the efficiency there is no difference between bolt and rivet, but the big difference or the main difference between the rivet and bolt and nut is that rivet joint is a permanent joint. So we have to broken the joint if we want to disassembly the component. But if we use the bolt and nut, it is not permanent joint. So it is easier for us to assembly or disassembly the component. That's the main difference. but because the refit is permanent joint, so the joint is very rigid. That's why it is used in the aircraft body because it is very rigid. So instead of bolt and nut, the body of the aircraft is joined by the rivet. We cannot imagine if the bolt and nut become loose because of vibration during flying. It will become a very big problem if the joint become loosened because of bolt and nut. It's not very rigid. Okay, so it is there is no difference in efficiency, but there is the difference between bolt and nut in rigidity term. Okay, so that's how we see the difference between bolt and rivet. And about weld, it is also permanent joint, and it has continuous joint area, so it will have larger joint load distribution. So it will be it will have higher efficiency. Okay. So theoretically, it will have higher efficiency compared with the rivet joint. But as we know that not all material can be joined by welding. So if you have very thick or very thin plate, then it will be difficult to join by the welding. Okay. Or if you have different parts, for example, composite and aluminum, we cannot use welding joint to combine this component. Okay, because it is they are not weldable. Okay. So that's even though the rivet joint has lower efficiency, but it can join those kind of material. So that's why we choose rivet joint instead of welding. Okay, so that's the answer is son.
Thank you, sir. And an additional question about the four students, sir.
Hmm?
Do you mind naming them?
Oh, okay. I will send the list to Edgar. Okay, I will make the list. It will need time to check one by one. Okay.
Okay, sir.
But I know there are 4 students have not submit the assignment. Okay. In the class we have 40 students, but the assignment submitted on the 36. So that's why I know that there are 4 students not submit their assignment yet. I will send the name to Edgar, okay? To the class leader. Okay, so if there is no question, I want to discuss about the class that I skipped last week. Okay, so because Edgar said that all of you have difficulties to synchronize the time for this class, so I consider to make a tutorial video about this rivet joint. So please wait for 2 or 3 days. Then please check the classroom. I will post the video tutorial about rivet joint, and give you some assignment for practice how to calculate the join by yourself. So I hope that you can do this exercise by yourself so that in the next meeting, if you have any problem during your exercise, then you can have a discussion. Okay? Is it okay for you?
Sir,
Yes, Isan?
the PowerPoint is not downloadable, sir, in classroom. Can we
Yes.
have the file?
No. I don't have the file because I create the slide directly using HTML5 in the classroom. So I don't have any backup. Is it better for you if you have your own slide or downloadable slide?
I think it will help, sir.
Oh, okay. Okay, I see. I will consider to make presentation using PowerPoint. Okay.
Thank you very much, sir.
You're welcome, Isan. So, thank you for joining class today and see you next week. Okay, Assalamualaikum.
Waalaikumsalam warahmatullahi
Waalaikumsalam. Thank you, sir.